Good morning, students. In today's session, we are going to discuss crystal field theory related to coordination compounds. Crystal field theory of coordination compounds. Okay. Before crystal field theory, we have studied Werner's theory and valence bond theory. Both these theories assume that the bonds between metals and ligand, the bonds between metal ion and the ligands are covalent bond, that is coordination bonds. But in crystal field theory, the main assumption is that the bonds between metal ion and ligands are purely ionic. Means these bonds arise due to the electrostatic interactions between central metal ion and the ligands. Is these bonds arise due to the electrostatic interactions between central metal ion and ligands. Okay. This theory also believes that central metal ion is a cation and the ligands is a point of negative charge. CMI is the cation and ligand as a point of negative charge. If the ligand is an anion like Cn minus, C2O4 2 minus, then the negative ends means then the atom which is carrying negative charge will point towards the CMI, central metal ion, and if the ligand is a neutral molecule like NH3, CO, in this case these molecules are polar, they carry a dipole moment. So their negative ends means their negative poles will point towards the central metal ion. Now the next assumption is this theory believes that initially all the 5d orbitals of the central metal ion are degenerated, means they have equal energies. So, ligands affect the relative energies of d orbitals of the central metal ion. In a free central metal ion, all the 5d orbitals are degenerated, that is, they have equal energies, but with the approach of ligands, this degeneracy is disintegrated, that is disturbed. This degeneracy is disturbed and the 5d orbitals is split into two sets. One is T2G set, in which dxy, dyz and dxz orbitals are there. And second is EG set, in which dx square minus y square and dz square orbitals are there. As we know that the 5d orbitals are dxy, dyz and dxz, dx square minus y square and dz square. Out of these three orbitals fall in this set, these three orbitals form this set, T2G set, and these two orbitals form EG set. What is the meaning of two different sets? This set will have different energy, this set will have different energy. Means these 5d orbitals now divided into two energy groups. The energy of the one set will be lower and the energy of the second set will be higher. But which set of orbitals will have less energy and which set of orbitals will have higher energy depends on the geometry of the complex. One more point is there, that ligands are the points of negative charges. So these points of negative charges arrange themselves around the central metal ion in such a manner that the repulsions between them should be minimum. Normally ionic bonds are non-directional, but these bonds are directional due to this point. Now, as I told you that according to crystal field theory, in the influence of ligands, the degeneracy of d orbitals is disturbed. Two sets are formed. One is of lower energy, one is of higher energy. And this degeneracy is different in the different types of complexes according to their geometry. So first we will discuss this degeneracy for octahedral complexes. In case of octahedral complexes, the T2G set, that is dxy, dyz and dxz, these orbitals are at the opposite side, and the EG set means dx square minus y square and dz square falls just towards the ligands. Means the ligands are pointed towards the EG set. Due to this, EG set gets higher energy and T2G set gets lower energy. So splitting in such a way that T2G set is now of lower energy and EG set is now of higher energy. higher energy. Okay. Now the difference between the energies of these two sets. Difference between the energies of these two sets is called crystal field splitting theory. Crystal field splitting theory. Why crystal field? Because this theory believes that the bonds between central metal ion and ligands are purely ionic. Means these are the bonds, these are the interactions, just as the interactions present in an ionic crystal. That's why it is called crystal field theory, and this field is called crystal field. Suppose if the average energy is X, average energy of these 5d orbitals is X. It means total energy is 5X. Okay. Now let's consider that the difference between the sets energies of the set orbitals is represented by delta naught. Delta naught. Now the energies of each of these orbitals will be decreased by 0.4. 0.4, and as it is decreased we will say minus 0.4 delta naught. Alright, and the energies of this set, orbitals of this set, increases by plus 0.6 delta naught. Okay, now as the law of conservation of energy, the total energy should remain conserved. Here you can see these three orbitals, their energy is decreased by minus 0.4 delta naught, means total decrease is minus 1.2 delta naught. You can see this, and here the total increase is plus 1.2 delta naught. So total energy remains conserved, but it is split into two sets. One set of lower energy, one set of higher energy. Now according to this theory, ligands are also of two types. Each ligand have different effect on the energies of d orbitals. Some ligands have a strong field, some ligands produce weak field. The strong field ligands will cause more splitting, the difference between the energies will be higher, and some ligands produce weak field, splitting will be less, lower splitting energy will be produced. Okay, and I told you that difference between the energies of two sets is called crystal field splitting energy or crystal field stabilizing energy, that is CFSE. A strong field ligand can cause pairing of the electrons, weak field ligands cannot cause pairing of electrons. Actually, for pairing the electrons, a definite amount of energy is required, which is called pairing energy. Pairing energy, in which case the pairing can take place if CF SE is greater than or equal to pairing energy, then the pairing will take place, otherwise not. If CFSE is less than pairing energy, pairing of electrons cannot be done. Okay. As I told you, ligands are of two types: strong field ligands, weak field ligands. When pairing is possible, in case of strong field ligands, electron will get paired up in the lower set of orbitals, lower energy set of orbitals, means T2G set. In that case, the complexes which are formed are called low spin complexes if strong field ligand is there, and if pairing does not take place and electron goes into the higher energy orbital, then it will be called high spin complexes. When weak field ligand is there. Examples of strong field ligands are carbonyl group, cyanido, amine. Weak field ligand, all the halide ions, H2O, etc. I hope today's session was useful for you. In the next session, we will continue CFT for octahedral complexes, and we will check the configurations of the complexes which are having different number of electrons in the d orbitals. Thank you. Have a nice day.